Hello, class, and welcome to our very last section, 11.3, Evaluate and Graph Logarithmic Functions. Here we have four objectives, and we will be looking at converting between exponential and logarithmic forms, graphing logarithmic functions, using logarithmic models and applications, and using the change of base formula. Okay, when defining logarithmic function, the name itself will sound scary, and the way it looks also looks scary. So why is it that we even need this? So we have to understand that when I introduced the exponential functions, I was talking about the difference between power and exponents, right? Let me write that out here. And let's say it's x power 3, okay? And this is 3 power x. Now, in order to get this 3 off and just solve for x, okay? To solve for x, we use the root, right? If it was a square root, then we had the corresponding power that will undo it. If you had the cube root, the corresponding power will undo it. In this case, if the power is 3, then it's going to be cube root. If the power is 2, it's going to be square root, and so on. So we learned this option. Now, when we have x in the power, and if I want to solve for this x, we have no tool presently to be able to bring that x from the power down to the base so that we could get x equals something, right? So for that, we need a special operation, and that operation is called logarithms, okay? So when I say operation, it's just like a plus, minus, multiplication, division. It is important in such terms, okay? So it is a very important operation in order to handle exponents, variables in the exponent. And therefore, it's only natural that we talk about the logarithms in terms of exponential functions. Just like how we cannot talk about square roots without the squares, or the cube roots without the cubes. Likewise, we talk about logarithms, and this is the conversion formula that kind of tells us how one is equivalent to the other. So let me write it out here. This is how we write the logarithmic function, y or f of x, whatever notation we use, equals log, you just call it log, okay? This x that comes in line with the log, so you read them together, log x, and then the b base comes a little below the log because it's positioned off of the line, horizontal line there. So log x is in the same line, and b is little below. So you're going to read it as log x to the base b. Please read it correctly. That shows that you really have learned logarithms. If you say log bx and all that, people will immediately know you don't have any grasp about logarithms. Okay, so log x to the base b. That's what we need. So what happens here? Now, what we're saying is in this relation, right, y equals log x to the base b. Okay. In this case, they have the base a. Okay, I'm just going to use base b so that you can also see the connection there. X equals b power y. This means this double arrowed ends indicate that you can go both directions. Okay. Y equals log x to the base b is equivalent to x equals b power y. So as you can see, this little table here, or rather this picture here, tells you that the base a here becomes the base over here as the exponent. And the exponent in the right-hand side, the power y, goes over to the other side as the part of the equation. Well, it's a little confusing this way, but when we look at a problem, we will begin to understand that. Okay, let's take part A. 2 power 3 equals 8. Is this in the logarithmic form or is this in the exponential form? So to understand that, let's quickly look again at our conversion here. Okay, let me call this the golden rule. Okay, because without this rule, without this conversion rule, you really cannot go between the forms. Okay, now on the left side of the rule, you see the word log, right? Of course, log. That means this is the logarithmic form on the left. On the right-hand side, you see the power, the exponent. So that must be the exponential form. And often, we may have to switch from one form to the other to make sense of it, to go further and solve it and so on. Okay? That's why this is the major bridge that will help you get between the two sides. So when you have the logarithmic form and you can't handle it, you will switch it to the exponential form and then begin to work with it. Now, if you have the exponential form and you're trying to solve for a variable in the power, then this logarithmic form helps you to solve for it by switching to this form. Okay. All right, so here they say convert to logarithmic form. Okay. And so you have 2 power 3 equals 8. Okay. So I would like to look at this so that it matches with the exponential. This is the exponential form. So I'm going to match it with the exponential form I have. X equals b power y. So that means b power y equals x, right? That's how this should look. So in this form, b is 2, y is 3, and x is 8. Right? I don't like to write it out like that, but because I'm trying to explain it here for the video, I have them written out like that. Okay? All right, so look at these positions and then convert them to the template that is the logarithmic form. So we're saying this is, I put the equivalent symbol here. This is the same as saying y equals log x to the base b. Okay. Now we know that from this relation here, y is actually your 3, log is log, x is 8, just based on the template. I hope you're tracking with me. And the base is 2. So we're saying log 8 to the base 2 equals 3. Again, the language is a little confusing. We successfully converted it to the logarithmic form, which is totally fine. But what does it really mean? Okay. Well, let me write the meaning here. Okay. Log 8 to the base 2 means you're asking yourself 2 power what equals 8. That is the meaning of this. Okay. Log 8 to the base 2 means this base 2 power what will give me that 8. Yeah. And then if you consider different options, you'll immediately notice that 2 power 3 equals 8 fits the bill. Okay. That's what we got here. We said log 8 to the base 2 is actually a 3. Yeah. So that 2 power 3 gives me an 8. So every time you do this, you're going to ask this question, the base power what will give me that 8. Okay. And there will be problems asking you to go in the opposite direction as well. They'll give things to you in the logarithmic form and ask you to write it in the exponential form. So you will be doing the reverse. You'll just be retracing the steps bottom up. Okay. Now let's look at B. 5 power half equals square root of 5. Again, this is in the exponential form. And this is clearly of the form b power y equals x. Right? That means your b actually stands for the 5. Y stands for that power, which is half. And x stands for square root of 5 itself. Now that you've got this, you can go ahead and fill the template. Okay, so that's going to be y equals log x to the base b. So we'll replace all these positions now. Y is half. Log is log, x is square root of 5, and b is 5. Okay. So this means 5 power what will give me square root of 5. Okay. And the answer is half. 5 power half is square root of 5. Okay. Again, this is slightly stammish. We haven't really dwelt too much on the square roots and the powers. But nevertheless, you do have this bridge here that helps you to make this connection. Okay. Well, anyways, what I'm trying to again point out is we are tracing our steps back to the original question. The original question did have that 5 power half equals square root of 5. That's what we arrived at here. Okay. And let's look at C. Half power x equals 1 over 16. Okay, so let's recognize that this is in the exponential form. So I match the correct form, which is b power y, and this side is like the x. The one that has the power, the exponent, is going to be that. And recognize that b is the base, which is the half. Y is actually the x here, and the x is actually 1 over 16. Okay, it's a good question because you are really being very clear-headed about how the positions are replaced. Okay, y equals log x to the base b is the conversion, and y in our problem actually is the x, equals log x in our problem is 1 over 16. Okay, and b is half, and because these are kind of large numbers, they're written in a bigger way. You want to really space them out correctly. That is your logarithmic form. Okay, so please practice on these forms and try to go from logarithmic form into exponential form, the reverse direction as well. Next, we move to graphing logarithmic functions. And we have seen with exponential functions that we just have to give different x's and then plug them in and find your corresponding y's. Okay, a quick, we need to know how this graph will look, right? So let's do a quick recap. Exponential function. We said that exponential, as the name says, starts slowly but grows rapidly, right? It goes like this rapidly. And it's in blue here. Okay, it grows rapidly like this. So we were talking about airplane takeoff. Now, when it comes to logarithmic functions, we must understand that logarithmic functions are the opposites or the inverse of the exponential function, meaning they will undo each other. These will undo each other, right? That's what we understood from the conversion above. That means it's the opposite of what is happening in exponential form, okay? So the opposite of this would be that it climbs rapidly and then moves slowly, okay? So then let me write it out here, okay? Here it is slow, and then here it climbs up fast, right? But the opposite of log is that it climbs up fast in the beginning, and then it slows down. Okay, let's make it very, very clear. It's slow start, fast pickup. This is fast start, then slowing down. Okay. So keep that in mind. That's the opposite of log. Okay, I'm sorry. The log is the opposite of exponents. So coming here to graph. Now, if I were to give some number log x to the base 2, unless it's an advanced calculator, most of our calculators cannot do that calculation because it's not programmed that way. So, in fact, the calculators are programmed to have the base as 10, not as 2. Okay, and using the calculator here would be completely unhelpful. So then what we're going to do is we're going to write this log x to the base 2 in the exponential form. So let's do this in reverse. Okay, so we need to write this in the opposite or the exponential form, which is the base power y 2 power y equals x. That's what you get when you do the conversion. Okay, you can try the conversion, but if you can also recall, y equals log x to the base 2. When you're converting it, right? This is the same as y equals log x to the base b, right? And that in the conversion formula is x equals b power y. But here, the b actually corresponds to the 2. So x equals 2 power y. That's what I have here. Okay. Now, because everything got switched, right? what we do in our table 2 will get switched. What this means is, now if you look at this, this is saying x equals 2 power y. So instead of generating values for x, if I generate values for y, it's easier to plug in for y as the power and get the x corresponding x, isn't it? So that's what we're going to do. We're going to fill in the y values first. Okay. So let me start with negative. Negative 2, negative 1, 0, 1, and 2. Let's plug that in for the 2 power y under the x column. Please watch out. That's really crucial. Okay. You're starting with the y, and then we are filling the x by plugging it in. Okay. So that will be 2 power negative 2 for the x, 2 power negative 1, 2 power 0, 2 power 1, 2 power 2. It's the exact opposite of what we did for exponential functions. So you have this similar setup under the y column there. Anyways, so that's a negative power. So flip the base, change the sign, 1 over 4. The rule is to flip the base, change the sign, 1 over 2. After this, no negative powers. So 2 power 0 is 1, 2 power 1 is 2, 2 power 2 is 4. Very nice, we got that. So now let's write this as 1 over 4 comma negative 2, 1 over 2 comma negative 1, 1 comma 0, 2 comma 1, 4 comma 2. Okay. So actually the coordinates got switched. If I were to graph these two on the same grid, you will see how well switched they are, exactly switched they are. All right, let's use red for this. Negative 4, 1/4 and negative 2, 1/4 and negative 2. So 1/4 is on the x-axis in the first box. I'm taking 1/4 and going down to negative 2. 1/4 and negative 2. Then half and negative 1. So right in the middle, half. Half and negative 1. 1 comma 0. That's right there. 2 comma 1. And 4 comma 2. You can see that the shape is beginning to come up as we expected. So it's climbing rapidly, and then it slows down after a while. And this is the graph for y equals log x to the base 2. See, now we actually graphed the log function, but we cleverly switched it to exponential function and did all the plotting of points. And then when we come back to name it, we always name it using the original function given to us. Okay. Let's try another similar one, but this time the base is slightly different, right? So y equals log x to the base half will be rewritten as half power y equals x. Okay, I'm doing the conversion already. Remember that was b power y equals x. B is nothing but your half. Your base is your half. Okay, once again, we're going to substitute, plug in values for y. So do the y column first. Plug them in here in your x column to get the corresponding x's. So that's going to be half power negative 2, half power negative 1, half power 0, half power 1, half power 2. Okay, this has a negative power, so same story, flip the base. So 1 over 2 is the base. When you flip it, it becomes 2 over 1, which is 2. And change the sign. So it becomes a plus 2. Or rather, let me just put a 2. It looks strange to have the plus 2. So 2 squared is 4. Again, flip the base, change the sign, just 2. Anything power 0, so it could be half also. So, right, half power 0 is 1. Half power 1 is half. Half the whole squared is half times half, which is 1 over 4. Let's put them in coordinates here. 4 comma negative 2, 2 comma negative 1, 1 comma 0, half comma 1, 1/4 comma 2. Okay. Let's quickly look at this. This looks pretty much inverted with this one here, right? You had the 1/4 comma negative 2, but here you have that 1/4 pairing with the 2, not the negative 2. Likewise, in the very last one is 4 comma 2 in the previous one, but here it's paired with 4 and the negative 2. So you can see that, that slight change happens when your base is fractional. We'll go ahead and plot this. 4 comma negative 2, 4 and negative 2. 2 and negative 1. 1 comma 0. Half comma 1. That's right there. Half comma 1. And 1/4 comma 2. So 1/4 of that and 2. So you can see this one. Oops. This one comes down like this. It looks more like an L, right? That will be y equals log x to the base half. Okay. Quick comparison here, right? This one is fast and then slow, but it's from left to right, right? This one comes down fast and then slowly moves to the right. It fades out on the right-hand side. So they both are logarithmic functions, but the direction is different, right? This one climbs up fast and then slows down. This one climbs down fast and then slows down. So we got that there. Why do we need the logarithms and where do we use them? We use them in many places. Okay, we use them in chemistry to find the pH factor. We use them in earthquakes to measure the magnitude of the earthquake. We also use them in determining the decibel level of a sound. So out of the many applications, we're going to focus on the decibel level. This is their formula, so you'll be given the formula. Don't have to worry about memorizing this, because this is really not math. This is more physics. But these are real world, real life needs here. So that is how they determine if, say, for example, housing can be done very close to an airport. So how far should they be, or what kind of materials to use in the house to kind of control the sound level, the loudness level, and so on. So it's very, very practical. Let's look at this one. Okay, the loudness level D measured in decibels. So D is the loudness, right? Level of loudness or loudness level that's measured in decibels. That's dB. D lowercase b capital. It's all supposed to be maintained the same way. And it measured in decibels of a sound of intensity I. Okay, I stands for the intensity, and I is measured in watts per square inch. And that is given to you in this formula. So there are only two variables. All others are numbers and operation. The logarithm is an operation. They want us to compute the decibel level. Here comes the problem. Extended exposure to noise that measures 85 decibels, dB, can cause permanent damage to the inner ear, which will result in hearing loss. Okay, they're saying if you're exposed constantly, right, extended exposure, to noise that measures 85 decibels, it can cause permanent damage to the inner ear, okay, and that can result in hearing loss. So that is kind of the threshold, the level. What is the decibel level of music coming through earphones with intensity 10 power negative 2 watts per square inch? Okay, let's scan this question. This question is saying, what is the decibel level, right? This is what we need to find. So that is missing, meaning your D is missing. Decibel level is your D, right? That's missing. But what is given to us is the intensity 10 power negative 2, and that's measured in watts per square inch. So even if they didn't use the word intensity, you will catch it by its unit, which is watts per square inch. So we are asked to find D given I. Let's write the formula. D equals 10 log I is 10 power negative 2 over 10 power negative 12, right? Plugged in for I. Now again, PAM does work. So what's inside the parentheses is what you will do first. This is again cool because it falls back on the laws of exponents. So if you have the same base, but you have a division going on, you subtract the powers, right? So -2 minus, so top power minus the bottom power. The bottom also has a negative, so watch out for that. Top power minus the bottom power. Okay, we now have 10 log 10 power -2 plus 12, right? The minuses combined. I'm doing it pretty elaborately here. So 10 power log, 10 times log 10 power -2 plus 12 is 10. Okay, this is what we have. Now, as I mentioned before, logarithm, the calculator is programmed to have logarithm with base 10. Well, if you look at this one has no base written, right? If there is no base written, the base is assumed to be 10. Okay, I'll just write there. If there is no base written, it implies the base is 10. If the base is 10, that means it implies we can use calculator. Okay. So pull out your calculator and locate the log button. It says log on it, L-O-G. So what I see here is when I use the calculator, right? So there is a log button. When you press the log button, again, learn your calculator, understand your calculator. Sometimes it accepts the entry backwards. I don't recommend those calculators. Look for calculators that have good display and it accepts the way you see it written. Anyway, so when I do the log button, it gives me as log with open parentheses. Okay, so it already displays that. So what you have to do is you have to enter 10 and then the power button and the 10. Okay, that's what you will do, and then hit enter. That answer comes out to be 10. Okay, there's already a 10 outside, but this answer actually comes out to be a 10. So 10 times 10 is 100. So D is 100 dB, decibels. So coming back to the question, we answered the question, but do you think this is a good level? Look at that. Extended exposure of noise that measures 85 decibels can cause permanent damage to the inner ear. But this one is saying 100 decibels that's coming through the earphones of that intensity, especially when we want very clear, crystal clear music, and we want all the effects of it. It's very likely that the intensity is adjusted to suit that, and that will increase the decibel level. And this definitely is scary because this says, I will just say unhealthy loudness level. Okay. Anyways, we are able to come up with that number by using logarithms. Let's look at this problem. What is the decibel level of traffic city or of heavy city traffic with intensity 10 power -3 watts per square inch? Again, intensity is given to us. We're asked to find the decibel level. D is missing. Let's write the formula. D equals 10 log I over 10 power -12. And in that formula, I'm going to plug in for I, which is 10 power -3 over 10 power -12. Very, very similar to the previous problem. Subtract the powers, so top power minus the bottom power. Ten power log 10 power -3 plus 12. Okay, so go ahead and simplify that. That comes out to be 10 log 10 power 9. Okay, again, use your log button in your calculator and then do 10 power 9. You begin to see a pattern. Okay, this actually returns a 9, right? The log and the 10, as if they're gone and you're just left with a 9. Actually, there is a rule, there's a property of logarithm that relates to that. Because we are non-STEM, we did not have to go into details about that. So we could actually execute this using the calculator, and therefore we have this. The D is 90, or the 90 decibels. So as you can see, they're asking us what is the decibel level for heavy city traffic. We can say the decibel level is 90 decibels for heavy city traffic. Okay, so much for the applications of logarithms. Well, we're only looking at the decibel application. There are plenty other applications too. The last section here is to do with change of base formula. Okay. Now, remember that your calculator, you really cannot forget this, calculator is programmed for log with base 10. Okay. If it has base 10, we call it the common logarithm. Because 10 is the common base that we use, right? Because our digits are we have 10 digits, right? 0 through 9. So that's the common log. So universally, we use we use this base. But there are other applications like computer science and other number systems that do not have 10 as the base. Okay, like computers has binary base system, right? 0 and 1. So for that, the base would be a 2. So other bases are practical for specific industries, for specific situations. But 10 is the common logarithm we use, and therefore it's called common logarithm, and calculators are programmed for that. When you have log with a base e, remember e is to do with life, right? Natural things. So that's why it's called the natural log. Okay, let me write it out here, log. Okay, and your calculator can be used only for these two situations. Okay, now when the log takes the base e, let me erase this a little bit here. When the log takes the base e, we don't write log to the base e because that's the whole point. The calculator does not have provision to enter the base. And so this would simply be ln. So you'll see an ln button in the calculator. ln stands for log natural, which is natural log. And log to the base 10 is common log. And so you will simply see the word log without any base in your calculator as a log button. So log with no base is the same as saying log with a base 10. Okay. Now, because of this limitation, if you have any other base, you cannot use the calculator. But this change of base formula takes care of that. The formula is so simple and so practical to use. So what it says is, if you have log m to the base a, just separate them to whatever base you want as log m over log a. So if you want the base 10, you can switch both the numerator and the denominator to that base 10. If you want it to be base e, then log to the base e is written as ln. Okay. And if you want a different base, then you could use log m to that base. Okay. Okay, so now our question is log 35 to the base 4. Okay, we want to use the calculator. So that means we only have two choices, either change it to the base 10 or change it to the base e. So we're going to do both, okay? So I'm going to do it to base 10 here. So the change of base formula says log 35 to the base 4 can be simply written as log 35 to the base 10, but I'm not writing it because you're not supposed to write it explicitly, over this log 4. So log 35 over this log 4, as simple as that. Now use your calculator, okay, and they want us to round to 3 decimal places. So, so log 35, okay. Again, I want to give you the values separately so you're tracking with me. 1.5, you shouldn't be reducing this or rounding this in any way. Keep it the way you see it in the calculator. But this again is for you to see. My calculator only displays this many digits, but you know it doesn't end there, it goes on, right? And then log 4. Okay. That will be 0.6020599913. Okay. Now again, as you can see, it's kind of too long for you to even enter the calculator. So just keep it as log 35 division, use the division symbol, press log again and enter log 4 and close parentheses as per your calculator. That gives me 2.564641,508. But remember, the question wants us to approximate it to the third decimal place. So look at that. And then that becomes 2.565. That's your answer when you use the base 10. Now let's try this for base E, okay, natural base. Let me also write it there, common, this is natural. For all life-related calculations, the natural log is mostly used. Okay? So especially in biology and sciences that relate to life, they automatically use ln, and that's how most of the calculations work. Anyway, so log 35 to the base 4, if I want to change it to natural log, that'll be ln 35 over ln 4. Again, ln stands for log to the base e. Okay? These are all crisp ways of writing the same information. So now go to the ln button, not the log button, ln button, and enter 35. Log, ln 35. That gives me 3.555348061. Okay, and ln 4 gives me 1.386294361. Okay. Again, as I mentioned before, I advise you to keep them all on the calculator. Just do ln 35 close bracket, parentheses, division symbol, ln 4 close parentheses, and that will give you 2.564641508, which is approximately 2.565. Now, isn't that clever? Both these answers actually, when rounded to the third place, they gave us the same answer, exact same answer, when rounded. But even before rounding, they came very close, right? Again, in my calculator, based on the numbers that were displayed, actually it was accurate throughout. This is the reason why the calculator is designed to, or programmed to have these two, because these two are comparable, they're very close, and you could use them interchangeably in some cases. And there's a reason why common base and natural base, they are close to each other. Okay, they work similarly in certain cases. But most of the times they will work very closely, the numbers. We even saw that in that compound interest problem, where we got the numbers slightly different, but it was still comparable. It wasn't too far apart. Let's try this one. Log, okay, let me do base 10. So log 46 to the base 5 would be log 46 over log 5. No base written explicitly, so you know it's base 10. This time, you're going to do the calculation on the calculator, and the answer comes out to be 2.378868 and so on. But we're rounding it to third decimal place, 3 decimal places. So that comes out to be approximately 2.379. And then let's do base E. Log 46 to the base 5 would become natural log 46 over natural log 5. So use the ln button. ln 46 over ln 4 on your calculator gives you 2.76178, so on. When rounded to 3 decimal places, 2.762. You notice that there is a slight deviation in the, oh, I'm sorry, I think I got the wrong number there. Pardon me here, because I think I did a log, a natural log 4 instead of natural log 5. That's why I was wondering why the big deviation. Pardon me on that. Okay, so ln 46 over ln 5, not 4. Yes, that's better. So I get 2.378868, 6 and so on. Now, isn't that interesting? Because when we didn't get the exact match. It can deviate a little bit, but for these small numbers, it shouldn't deviate that much, and that caught my attention, and we went back to fix it. Okay. 2.379. And this is the reason why it doesn't direct you as to what base to use. It's just saying round to 3 decimal places, approximate this. So when you approximate it either using base 10 or base E, you get the same answer. Okay. So I hope this lesson was interesting. And with this, we wind up with all our sections. And this is the end of our course. It was fun and very entertaining for me to create these videos. I thank you for your patience, and I really look forward to your success in life. All the best.